Now that we have studied all the gas laws, it is time to include Avogadro's principle in order to talk about the ultimate gas law, the ideal gas law. Avogadro's principle relates the volume of a gas to the moles of a gas. The more moles of a gas you have, the larger the volume if pressure and temperature are constant. The less moles of gas you have, the smaller the volume if pressure and temperature are constant. So there's a direct relationship between volume and moles. So now if we take Avogadro's principle and we incorporate it with Charles' law and Boyle's law, we can make a new proportionality that includes moles, temperature, pressure, and volume. If we include a constant, we can make the proportion into an equality. Then we can rearrange to get what's called the ideal gas law. Now, we don't use K for a constant. The ideal gas constant is called R. And if you rearrange it, you get PV equals nRT. That is called the ideal gas law. Unlike the other gas laws, specific units of pressure and volume have to be used when using the ideal gas law. And this is because of the gas constant. The gas constant is 0.08206, but the units on that constant are liters times atmospheres over moles times Kelvin. So in order to get those units to cancel appropriately when using the ideal gas law, the pressure has to be in atmospheres and the volume has to be in liters. As with all gas laws involving temperature, the temperature must be in Kelvin. This is very important. If you use the wrong units, you'll calculate the incorrect answer because you don't get your units to cancel in the gas constant. Using the ideal gas law, you can come up with that constant that we've been using since the first semester. 1 mole of any gas at standard temperature and pressure occupies 22.4 liters. To demonstrate the effectiveness of the ideal gas law, we are going to perform a little demonstration. We are going to collect a gas over water. And a gas collection tube, the fancy name for a gas collection tube, is called a eudiometer. So we're going to use a eudiometer and we're going to do a little reaction and collect a gas over water. The reaction we're going to observe involves taking magnesium, reacting it with hydrochloric acid, and collecting the hydrogen gas that's formed. We also produce MgCl2. The overall balanced equation involves 1 magnesium, 2 HCl, 1 H2 gas, and 1 magnesium chloride. Now, if we have a certain starting amount of magnesium and it reacts completely, we could just do the old-fashioned way to determine how many moles of gas form. We could just use stoichiometry. So this will be a way for us to check our answer using the ideal gas law. As you can see here, we have a piece of magnesium that is 0.034 grams. If we start with what's given, we can use the atomic mass of magnesium to convert to moles of magnesium. Our grams cancel, and now if we want moles of H2 instead of moles of magnesium, we just use the mole ratio from the balanced chemical equation. It's 1 to 1. Our moles of magnesium cancel, and if we solve this, we get that many moles of H2. However, that has too many sig figs. If our mass only has 2 sig figs, then our moles of H2 can only have 2 sig figs. So after we perform the experiment and use data from the ideal gas law to find the moles of hydrogen gas, we should get 0.0014 moles of hydrogen gas. For this reaction, we need all of the magnesium to react with excess hydrochloric acid. So we're going to start by taking this magnesium and coiling it up tightly in this little copper wire attached to a stopper. Now we are going to add 10 milliliters of 6 molar hydrochloric acid to the eudiometer. Then we will add water to the tippity top of the eudiometer. Now we put the stopper containing the magnesium in the eudiometer and we invert it into this beaker of water. The HCl is more dense than water, so it will start to trickle down the tube And when it comes in contact with the magnesium, you will see the reaction start to happen as hydrogen gas forms. After all of the magnesium has reacted, we are ready to collect the data to be able to use the ideal gas law to calculate the moles of gas that were formed. To get the volume, we first have to equalize the water levels inside and outside of the eudiometer. To do this, we need a little bit bigger piece of glassware, so I'm going to transfer the eudiometer from the glass beaker to this large graduated cylinder. When we equalize the water levels inside and out, we can see that we have a volume of gas of 33.10 milliliters. We will assume the temperature of the gas is the same as the temperature of the water it was collected over, so the temperature of that water is 19.1 degrees Celsius. Because we equalized the water levels inside and outside of the eudiometer, the pressure of the gas inside the tube was the same as room pressure. So we can use the barometer to get room pressure, and we can see here that the room pressure is 721 millimeters of mercury. Now, because we collected this gas over water, that volume of gas is not just hydrogen gas. There's also some water vapor in that gas sample. So we have to account for that water vapor. So we can use this table here that gives us the vapor pressure of water at all these different temperatures. Since the temperature of the water was 19.1 degrees Celsius, we can find approximately where that would be on the table and come up with the vapor pressure of water that would be in that sample. It's around 19, so we know it's around 16.5. Well, we were 19.1, and if we look, 19.5 is 17, so it seems to be going up by a unit of 0.1, so 19.1 we'll call 16.6 millimeters of mercury for the pressure of water that is collected in that gas. So to get the pressure of just the hydrogen gas, we can make use of Dalton's law of partial pressures. Okay, I'll explain this more in a second, but basically the total pressure of a sample of gas is equal to the individual pressures that make up that gas. So we have two gases in the tube. We have water vapor and we have hydrogen gas. Well, I know the total pressure is 721 millimeters of mercury, and I know the vapor pressure of water is 16.6 millimeters of mercury. So to find the pressure of just the hydrogen gas, I can subtract those. So the pressure of hydrogen gas is 704.4 millimeters of mercury. So let's talk a little bit more specifically about Dalton's law of partial pressures. If you have a constant volume of gas and the temperature is also constant, the pressure of each individual gas can be added together to get the total pressure. So for example, if you have a sample of oxygen gas exerting a pressure of 159 millimeters of mercury, and you have the same volume of nitrogen gas at the same temperature exerting 593 millimeters of mercury, if you were to insert those two gases into the same container, so they have the same volume at the same temperature, you can get the total pressure exerted on the container by just simply adding the pressures of those two gases together. So in this case, you would take 159 millimeters of mercury plus 593 millimeters of mercury to get 752 millimeters of mercury. So how does that apply to what is happening in our tube? Reaction here occurs here on the left. We got the bubbles of hydrogen forming, so this is when the reaction is still going. When it's all done, we equalized the water level inside the tube and outside of the tube. We had this volume of gas in the tube. This wasn't just hydrogen gas. It also contains some water vapor. This occurs anytime you collect a gas over water. You have to account for the vapor pressure of the water. So there's a lot more hydrogen than there is water. So we'll put some hydrogen molecules in here, but there are still a few water molecules. If you don't account for them, the analysis of your data will be very erroneous. You will have large errors. So you have to account for the water vapor. So this is what's actually in our tube. We have some water molecules, and we have a lot of hydrogen gas. Remember, we make the water levels equal inside and out, and the reason we do that is because the pressure of the gas inside the tube is then equal to the external pressure. So then all we have to do is look at the barometer to get the external pressure, the total pressure. Then we know that if we take the pressure of the hydrogen gas plus the pressure of the water vapor, we can get the room pressure, the same as the external pressure, because we will know the water vapor pressure using our table, and we will know the room pressure using the barometer, so we can rearrange that equation to get the pressure of hydrogen gas. So when we did it, we took 721, which was the total pressure, the room pressure, minus the vapor pressure of water, 16.6, and got 704.4. Now that we have all of our data collected, we can use the ideal gas law to determine the moles of hydrogen gas that were collected. Remember, we should get 0.0014 moles of hydrogen gas collected. So we're going to use PV equals nRT, but we're going to solve for N. We're going to have to divide each side by RT. That gets us an equation of N equals PV over RT. Remember, all of the data has to be in a specific unit. Pressure has to be in atmospheres. So we can take the pressure of the hydrogen gas, 704.4, and divide by 760. Just a quick reminder, we got that 704.4 by taking the room pressure minus the pressure of the water vapor. So now we have a pressure in atmospheres. The volume needs to be in liters, so we have to take that 33.10 milliliters and convert it to liters. R is a constant. It will always be the same, 0.08206. And our temperature is 19.1 degrees Celsius, but it has to be in Kelvin, so we have to add 273. Now we have our data in the appropriate units. We can plug them in to the ideal gas law, and we can solve for moles. So when we do that, we'll plug in our pressure, our volume, our constant, and the temperature. You will see all the units will cancel except for moles. When we calculate the moles here, we get 0.001280 moles. How many sig figs can we have? Well, if we look at the numbers that we ended up plugging into our ideal gas law, ignoring the constant, we can have 4 sig figs. So the number we solved for there, that is the correct number of sig figs as well. So we were supposed to get 0.0014, and we got about 0.0013. I'll take it. That's pretty good. That is less than 10% error. I'm pretty happy with that. So you can see here that the ideal gas law works. No matter whether we solve this problem with stoichiometry or with the ideal gas law, we get the same answer.